a magnet kept in an extramagnetic field. If it's kept so, say this is north and say this is south, we know that there is a force to the right and over here left. What happens? This forms a couple and it will rotate. So after a second, what happens? So it will align in this way. So what does this mean? This means that it had potential energy. And in this video, we are trying to figure out this potential energy. How do we generally do that? We do work against the field. That will be our work. And see how much work that we have done. So measure that. And we know that this force is conservative in nature. So this two will be equal. Which two? Work and the potential energy will be equal. Whatever work we have put in rotating this, that will be the energy that the magnet or the system will have. So when we derive this, we'll look at specific scenarios. So for that, we'll consider 90-degree as your reference angle. That will be something that we'll be talking about, but understand that by placing the magnet in this way and then rotating to a particular angle, the amount of energy that we spend in doing this, that will be your potential energy at that particular angle. That's what it means. So basically at this point, it is zero. The energy is zero. And there is gain, if not loss of energy when we shift it around. So that's about your reference angle. We'll see that in a second. So the derivation will start like that. We'll consider a power magnet of length 2L placed in a uniform magnetic field of B. Then the charges over here is Q. So the force will be QMB minus QMB. So let the magnetic axis of the bar make an angle of theta. So this is theta. And what will happen? It will rotate. Is it not? So that's what we are looking at. We're looking at the torque. So force and the ends are, the net force is zero. So there's no translation motion, but they're acting on different axes. So there is a couple. And this results in a torque, which is given by mb sine theta, which we just derived. Now, the torque tends to align the dipole in the direction of B. If the dipole is rotated against the action of the torque, work has to be done. This work is stored as your potential energy. So let's start by rotating it by a small bit. Say we have the magnetic field line in this manner. Say the magnet was in this way, wherein this is north, this is south. We will rotate it a bit. Okay, so that is your d theta. Your small work is equal to d theta. Is it not, guys? Because the torque by the magnetic field will be to the right, not exactly right, but clockwise. So we have to do work anti-clockwise. Agree? Next, this will give us a positive work. This will be a positive work. So I'm just talking about positive work. Yes, you can do negative work also, not an issue. Now, the formula is the following. W is equal to integration of dW. That is, we are adding all the small bit of work because at every point, the amount of work done is different. right? So it will vary from theta 1 to theta 2. So we can call it as theta I to theta f also, not an issue. And this is torque d theta. So when we substitute torque, which is equal to mb sine theta d theta, mb is constant, and we have mb integration of theta 1 theta 2 sine theta d theta. So this is mb integration of sine theta is correct minus cos theta 1 theta 2. So we'll end up with mb cos theta 1 minus theta 2. You just do the math, you'll get this. So please note that your textbooks or reference books, they might talk about minus of this expression, just that they're taken minus out from this particular bracket. Okay, again, both are right, just that I've written it in this manner. So I was talking about reference angle. Potential energy at a particular orientation is given by considering the initial point as 90 degree. So W at theta, or again U at theta, is given by mb cos 90 minus cos of theta. That's what it means. So this will be minus mb cos theta. This is basically nothing but your dot product. Agree? And so we have two more specific cases that we can derive from this. So your, just a second. Dipole moment is in the direction of magnetic field. So in this case, M and B are pointing in same direction. So in this case, what? In this case, we have U will be equal to maximum. Okay. Actually, it should be, sorry, this is minimum. So this will be minimum. It will be a negative value. This will be a negative value. Because MB cos theta cos 0 is 1. So it will be a negative value. This will be minus MB. While it is anti-parallel means theta will be equal to 180 and cos of 180 is minus 1. So V will be equal to minus MB minus 1. This will be MB. So this is a positive value. And this is nothing but your maximum value. So basically, what does it mean? You have to flip the magnetic field, not magnetic field, the magnet in this direction. Right? So we have the write-up from this point. Okay. So please pause, have a look.